So welcome to cross-product vector operator. In this video we are going to actually make the tanks not only move forward and backwards but be able to turn as well. By the end of it we will have some crazy situation, something like this, where these AI tanks are not exactly masters of their own movement, but they are moving and trying to get towards us despite all the slipping and flipping. So I will see you in there. So the first thing I'm going to do is pop into Visual Studio and just comment temporarily out the intend move forward without my insert key on, and just compile that back up. And what that's going to do is obviously just stop the tanks moving forward and backwards. I just want to focus on their rotation for a moment entirely so we can see that independently. So we'll freeze them in the forward backward direction like that, and now they'll just sit there again. They'll stay in aim obviously, but they're just going to sit there. Cool. So let's talk about how we want things to work with regards to rotation. So we have the AI providing this same vector, so this tank here right now would probably have a vector heading straight towards me, whereas if he was round the hill, then remember he may have a vector that takes him round the hill rather than straight towards me. And he has his local forward. Remember, you can use this little square for local stroke global. He has this local tank forward red vector here. Now the question comes, how do we decide how to rotate? We've done the forward and backwards, at least for now, and now we need to decide how to rotate. So the deal is that if the tank is already, if this guy was already facing us like this, then it wouldn't need to rotate at all. And if he was facing 90 degrees on, it would want to rotate as fast as possible. It's almost exactly what we were doing before, but like in reverse pretty much. So this is where the sine function comes in, very much like the cosine function. In fact, it's exactly the same shape. It's just shifted along by 90 degrees. So let's think it through. But firstly, what are the axes? Well, the x-axis is the angle between the AI forward intention and the tank forward, just as before. And the y-axis is the throw that we're going to pass, but this time to intend turn right rather than to intend move forward. So if there's no angle, i.e. if the AI forward intention is already aligned with its forward, if it's already facing in the direction the AI wants it to go, then how fast should we turn right? Not at all. If we are 90 degrees out, it's going to turn right as fast as possible. If we're 180 degrees out, it's not going to turn at all. Now we'll talk about that again in a second, because that seems odd, but it's okay. And if it's 270 degrees out, i.e. if it's on the right instead of the left or the left instead of the right, then we go in the opposite direction. So this should always turn us in the correct direction. So let's say that 90 degrees means that the tank wants to be going to its left, then it to its right, then that means it turns right at full speed. If it wants to be going behind where it is, then we'll talk about it in a sec. It looks like we do no turn, but we'll think about what happens. And if the thing that it wants to go towards is to the left of it, then it will turn right at a value of -1, i.e. turn left. Okay, hopefully I've gone through that slowly enough. You get the idea. Now let's talk about this bit where I'm precisely behind the enemy tank, i.e. it's sitting here. Let's put it in rotate mode with the E key, just as a reminder. If we're in this situation where I'm behind this other tank, what's it going to do? Well, the fact is I'm never going to be exactly behind it. These are floating point values, these rotations, and I'm moving and the other tank is likely to be moving forward or backwards. So I'm never going to be exactly behind it. And if I am exactly behind this guy, then the moment there's any deviation from being behind it, it's going to be unstable and it's going to move up to one of these other points. It's going to move away, right? So what's going to happen is that if I'm slightly to its left behind it, then it's suddenly going to turn left, and head towards me, or right, vice versa. So it's just going to move away from this point really quickly. It's not a stable point. So we don't have to worry about the fact that this curve makes it not turn when it's behind us. Right, so we need the vector cross product. It's more complicated. The vector cross product is this thing here. It is the magnitude of the two vectors that we're sending in, which remember is the same as before. These are these AI forward intention and tank forward things here. Let me just group these a little differently. Let's put forward throw right next to where we call intend move forward. Okay, so we can just see these two vectors as independent. Great. And then it's sine of the angle between the two, different to before by 90 degrees, we've just talked about that, times n, which is a unit vector perpendicular to the plane. It says the plane on Wikipedia. What it's talking about is the plane defined by A and B. So A and B create a plane, just like over in Unreal here. If we click on this dude, the red and the green arrows say define the ground plane. Blue is perpendicular to it. And the direction that it's in depends on the left-hand rule. If you put your left hand out now, and you put, say, your thumb along the red, well, let's do this so it's easy. Put your forefinger along the red line, your index finger, and then put your next finger along your middle finger on your left hand down the green arrow, and your thumb pointing upwards. That's the left hand rule. So the X is your index finger, the Y, the green, is your middle finger, and then your thumb, in this case, tells you which direction the Z would be in, or the N vector. So it is directional. Let's look at a table a bit like we had before. It takes two F vectors on the input, but the order of them matters now. The order that you cross these things in actually does matter. If you swap A and B around, then the direction of N changes. It swaps. The output's an F vector this time. Previously, we had a float. What does it do? It kind of measures perpendicularity. It tells you how perpendicular these guys. You get a maximum vector out of this thing when the two things are at right angles, and a minimum vector when they're parallel. So that's perfect. So when the AI forward intention and the tank forward are parallel, then you get 0. And when they are perpendicular, you get a maximum value. The vector you get out is always orthogonal to both. Orthogonal means pointing in the other direction. It's perpendicular to both of them, exactly like these axes. The only difference from these axes is, of course, the green and the red could squeeze in together or go opposite. And we'll look at that in a second. So in a diagram, we've got this. This is A and B down the same thing. This is us pointing at the enemy tank. This now is where we are. The enemy tank is precisely, or the targeted tank is precisely to our left. Forget the magenta line for a minute. In this case, the targeted tank is precisely behind us, and there is no turning going on. And then as the animated GIF comes round, this is where the targeted tank is on the right of us. Now, the magenta line is the cross product. So if it's on the right, it's demanding a rotation. It's representing a rotation. Now, it's weird that it's a vector, but that's just how it is, and you'll see how we use that in a moment. So in this case, there's no rotation, no magenta line. When we see a target on our left, we rotate as fast as possible to the right. That's what an upward arrow is going to mean. Rotate as fast as possible to the right to get back towards facing it. When it's behind us, we don't rotate at all, but as I've said, as soon as we start rotating, we'll continue rotating in that direction. And then if our target's on the right-hand side, then this arrow is representing us wanting to turn left as fast as possible. You can read all about that on Wikipedia if you want to find more about the cross product. But what I want to do now is get into actually using it. So just like before, you can do this, but I've just got one more thing to tell you. It's a vector that comes out of the cross product. And we also need to think about what would happen if the tank was on a hill. Let's say that we're not just constrained to a plane here, but this tank is kind of sitting up on the hillside like this and has fallen down and is, let's say, rotated a little bit because it's sitting on the hill. Then what are its vectors doing? Well, the forward intention vector may be a three-dimensional vector from this tank down to this tank, but the forward vector is here. But that's okay. The cross product will still be a vector pointing up something like the blue arrow. It'll be a different angle to the blue, but it'll be pointing up kind of up and right here. But it still has a Z component, a component in the world space up direction. So these two vectors let's go to the code. These two vectors that we're going to be taking a cross product of are both in world space. The tank forward and the AI forward intention are in world space. So whereas I've been demonstrating tank forward using the local coordinates, the tank forward as far as what we're getting out of the code is actually that red arrow there. So it's world space. And then the vector that we are getting for AI forward intention is also in world space, and in this case would probably be a line pretty much straight from this tank down to this tank. It would drive it down the hill. Okay, so what you get out of this, out of the cross product, is also should be interpreted as a world space vector. And it won't be parallel to the ground, but we can just look at its Z component, i.e. the component around the blue line here, to find out whether we should rotate left or right as far as gravity is concerned. So we're determining our rotations based on gravity. All right, let's put this tank back in terms of rotations. Probably the easiest just to reset the rotator here. I'm going to put it back in terms of location. And then I'm going to give you a challenge, which is I want you to cross AI forward intention and tank forward just like we did before. But find the Z component of the resulting vector, that's just a .z, and feed the result into intend turn right, then share the resulting movement with the community, ideally on community.gamedev.tv and the Unreal section under the Battle Tank subsection. See you soon. Okay, welcome back. So let's have a go at this then. So we're going to have an auto turn, or just call it right throw, equals f vector. It's a static method on f vector called cross product. These are really handy. You'll use these things a lot. So which way around do we do these? Frankly, we need to just try it. We could reason it with a left-hand rule and think about which way things are increasing, but it's much easier and quicker just to have the framework, which is if we get it wrong, it's going to rotate in the wrong direction, and try it one way. I actually got a feeling that what I'm doing is the wrong way, but I don't mind making that mistake. We can correct it. Okay, so I get the cross product between the two. Now, the right throw isn't just that, because look, these types are incompatible. The right throw is currently coming out as an f vector. You see that? Because the cross product returns a vector. The forward throw came out as a float, but the right flow is an f vector. That's why, well, one of the reasons why we need to take the z component of it. Now if we look at the type of right throw, it's a float. Intend turn right with right throw. Okay, let's try it. This may be the wrong way to be doing the cross product. And let's see the symptoms if it is the wrong way of doing the cross product. It's just simply quicker to try it both ways than in this simple case than it is to be working out what it should be. Now, is this guy turning towards us? No, not really. Let's try the other guy. Let's just move this other guy in front. Trying, but they're not really turning to face us. No, I'm not convinced. Let's just put him off to that side. Okay, I'm not convinced they're turning to face us. Let's try doing it round the other way. Recompile. And then if it works, what we'll do just very briefly at the end is turn the forward movement back on and see what the total movement looks like. Okay, let's have a look now. No, I think that's worse. Okay, so what I'm going to do is swap them back to how they were. And then I'm going to turn in the forward movement as well. And then let's compile that and see how the total behavior is. In fact, I'm going to get my controller on and get ready to run away from these tanks just in case it works. So play the game, F11. Okay, now let's see what happens. I'm going to move out the way, have a little look around. Oh, I'm very slippy. We'll sort the slippiness out later. How are these guys doing? Yeah, he's coming towards me, trying to broadside me. I think one of the reasons they're not behaving right, let's just have a look at the nav mesh. Hit P. Ah, look, there's a big hole in the nav mesh. You see that? This guy's sitting near an edge of the nav mesh, and if he slides into the hole in the nav mesh, then we're in trouble, because he's not going to be able to navigate any longer. So what I'm going to do just to sort that out very quickly is to go to the world, go to the nav mesh bounds, lift them up a little bit, let them recalculate so that this hole over here that this tank is near to gets filled in, and then replay the game. Hit F11 so you can see better. And this is fun. You see these tanks are being forced to use our control system. It's balmy tank battles here, and they're not, the acceptance radius isn't working at the moment in that they're coming all the way up to us. But look, we've got movement. We've got a kind of fun game. We've got weird AI tank behavior. They're chasing us and they're aiming at us. So congratulations on some sort of tank movement. We've still got bugs with them hitting the ground. We've got all sorts going on, but it's fun and the game is still fun. So this is what we're after. All right, see you in the next video.